So good morning, everyone. My name is Darin, and I'm really excited to be here today and sharing with you a little bit about my company, Silver Spring Networks' use of Apex's StatsListener to tune the processing rate of data ingestion for smart grid utility data. First, let me say a little bit about myself, and then I'll provide some background on Silver Spring Networks' data platform. As I mentioned, my name is Darin Nee. I'm a software engineer, and I lead the effort to implement DataTorrent as a stream processing tool for our team. And while I'm mostly a user of Apex, I've also made a couple commits to the Mulhire library. Now I'll tell you a little bit about Silver Spring Networks and the platform I work on. My company is a global IoT company based in San Jose. We provide smart grid products to both utilities and cities, and our software gets used to help customers improve energy efficiency. We've currently got more than 25.5 million network endpoints deployed on devices like smart meters and transmitting that data across mesh networks to our back office software products. While you probably don't look at your smart meter every day, if you did, you'd see Silver Spring Networks logo imprinted on it. So you may not have heard of us, but we are actually a household name. Now I'll talk more about our use case for Apex and the product I work on, which is called Silverlink Data Platform. The problem we face with our data is that it's siloed in different applications, making it difficult to derive meaningful insights. Our solution, typical solution, is to put all the data in one place and create a set of APIs to simplify access for apps built by us, by utilities themselves, or by third-party developers. We do it by automatically ingesting data and enriching it with contextual information in a Hadoop setting, and that enables both real-time and batch applications. Here you can see the scope of devices that the data platform solution encompasses. Some of the software products we currently use the data for. Using this solution, we've unlocked analytics opportunities and insights from data, things like detecting theft of electricity or anticipating meters that are likely to catch fire. What kinds of data specifically are we collecting over the network? Meter register readings are power usage data that utilities used to dispatch a human on site to report once per billing period. Nowadays, smart meters collect the time series of power usage, enabling utilities to charge differential amounts for peak and off-peak times. These time series data are called intervals and can be as frequent as 15 minutes or every 4 hours. We also collect threshold event data, such as voltage sags and swells, temperature-related events, and network traps. Sensor reads are another class of data that we ingest and could be as frequent as 10 seconds. Device metadata includes information like latitude and longitude, the NIC/MAC address, the device type, and network topology. It helps to understand how data gets from a device to our platform. The NIC is Silver Spring Networks' hardware component that radios data back across the mesh network to the utility back office software. Some data also gets sent asynchronously. We have agent software that runs in the back office of utility and forwards that data over HTTPS to our secure Hadoop cluster, where we use Apache Apex and other tools to do ETL and then output it to databases and formats that facilitate retrieval from using our APIs. We also have a SQL interface. This diagram shows what one of our Apex apps looks like. The logical processing flow is described by a directed acyclic graph, or DAG, as Pramod explained, composed of operators and streams. Here you can see the various labeled operators we use to read, transform, enrich, normalize, and persist the different kinds of data we work with. Specifically, this application periodically scans HDFS directories for new files, parses various types of CSV and XML files, and converts their lines or blocks of XML into tuples. And then it enriches those tuples with device metadata, which we store in Elasticsearch. It normalizes tuples into a common schema, and finally writes those tuples out in a variety of formats, for instance, rows in HBase, documents in Elasticsearch, and messages in Kafka, as well as files in HDFS. So that's a high-level perspective of our use case for this application. What I'd like to talk about is some specific strategies that real-world strategies that we used in building this application. So unless you work at Yahoo, you probably have a finite amount of resource you're working with in your cluster. This is a natural economic constraint that should be expected in the bootstrapping phase of any big data product. As such, we found ourselves looking to maximize performance given a fixed amount of cluster resource. We wanted to be able to process a day's worth of data in a short period of time, less than 1 hour, with at most a ½ terabyte of cluster memory footprint. So the basic Apex operator works in a synchronous style and uses the same execution thread to process a tuple from receiving it on an input port to emitting it on an output port. Apex then scales up processing for an operator using the classic Yarn application solution, which is to spin up more containers or partitions of the operator. But if the resource cost of a partition is, or of a Yarn container is 4 gigabytes, let's say, then you can see that it makes sense to be very prudent with partitions in the context of running a handful of applications, of Apex applications, each with its own set of operators in a cluster with a ½ terabyte of resource available. So asynchronous operators use worker threads to make better use of container overhead before adding partitions. One example where this makes sense to use and works well is when network costs are associated with the processing. Then having multiple clients, each on its own thread, transacting across the network can have a substantial performance improvement, and this happens before you need to partition the operator. So we use this design for retrieving documents from Elasticsearch to enrich our tuples, as well as for doing bulk writing of time series data points to HBase. A key point with this strategy is that it requires the use of a non-transient buffer for all of the input tuples to the operator, so that the operator can recover in the case of failure. And that's because Apex's checkpointing mechanism serializes an operator's non-transient variables. As a consequence, it also creates a problem when an asynchronous operator is subject to a highly variable load. For instance, we ingest files of greatly varying size. It could be a few kilobytes or many gigabytes compressed. And within those files, you can break them apart into tuples that themselves may have either thousands of intervals or none. In fact, some files contain different proportions of events and intervals, so there's a differential tuple mix as well. So all of these factors lead to the possibility of bursts of tuples on incident in an operator. if an asynchronous operator suddenly receives a very large number of tuples, its input buffer can get too big for Apex to checkpoint, and that results in an out-of-memory error and a killed container. As a side note, we couldn't use a blocking type of buffer because Apex automatically restarts blocked operators after a period of time. So what this leads to is the behavior is endless container cycling, since the fault-tolerant recovery mechanism launches a new container with the same conditions that led to the first failure. So obviously, that's a big problem in terms of going to production. We quickly realized that we needed a way to regulate or at least limit the flow of tuples through certain operators that are upstream of our bottlenecks, in this case, Elasticsearch and HBase. We found that implementing that was not hard at all. We added a throughput property to upstream operators and a buffer for tuples to emit. In this way, we could set reasonable limits on the volume of tuples per processing window that a downstream operator could expect to receive. And setting that limit on the input operator could regulate the entire flow. Again, the problem was that limits that stabilize performance also tended not to best utilize the processing capacity of the cluster. The DAG was operating at a trickle. So we could manually adjust the throughput using the Apex CLI, the command line interface, during runtime, and that was useful, but we needed a way to automate the tuning. Enter Apex's StatsListener. This mechanism worked adequately to provide a self-tuning throughput management system, or more simply put, backpressure. Really quickly, a StatsListener runs in the app master container, so not the operator container. It receives batches of stats at the end of each processing window from one or more operators, and it can respond with a set of commands to the operator, for instance, to update the throughput. So we programmed a model that keeps track of the total number of tuples that have been emitted by an upstream operator versus processed by its immediately downstream operator, and used those stats to compute both a backlog and a processing rate. And then we issued commands trying to maintain a backlog that's a multiple of that processing rate. So we also, as a side note, if the DAG is idle, we assume a default minimum processing capacity for each operator. And here you can see orange circles representing tuples and two processing windows. In the second processing window, the backlog is 4, and the processing rate was 2. If we were to assume a target backlog multiplier of 3 and a minimum processing capacity of 2, let's say these are in units of thousands to make it more interesting, then the next throughput would be 2,000, let's say. So we generalized this backpressure approach and implemented it across all connected pairs of operators in all of our applications. And the result was that we no longer suffered from containers running out of memory and cycling endlessly. In fact, we obtained good long-term stable performance, runtime performance. So the overall DAG processing rate adjusts automatically according to current constraints. This strategy has effectively solved multiple problems for us, since factors impacting performance for different operators include container garbage collection, HBase writes not keeping up, Elasticsearch request latency, and HDFS name node request latency. So that was a success, and it enabled us to get to production. More recently, I was very pleased to learn that DataTorrent took in some of our customer feedback and has built in a solution for backpressure for the next release of Apex. That's really great, and I'm looking forward to testing it. Thanks, everyone, for your attention and interest in Silver Spring Network's implementation of Apex. I have time for a few questions.
So you're listening, for
Right. So we aggregate across all the partitions for each, the stats that are reported for each partition of operator and aggregate them all into, is that your question? Into one summary statistic for the upstream. And, yeah. Yeah. Sure. Yes. The question is that different partitions of an operator may be receiving different load and needing to have customized throughput management as opposed to a logical operator as a whole. So our model at the level we've implemented it currently doesn't independently manage different individual partitions. It's actually just generalized at the level of the logical operator. Yeah. Good question. Yeah.
So you said the backlog is a certain multiple of the processing rate.
Right.
So what's the reason for that? I mean, it's just some arbitrary constraint, is it?
So we tested a couple different models, but this model proved to actually work, as opposed to a model where, for instance, you could have like a threshold that's a high threshold and a low threshold, and you try to move your processing rate between those two. That led to kind of a sinusoidal oscillating overall processing rate across the DAG. And there's control theory that you can look at, and what we ended up coming up with was this model as a multiple of the processing rate. And you can think, I like to think of it as always wanting to have, like always wanting to have work to do. So if I'm like in a agile Scrum, I want to have a backlog that's a multiple of how many tickets I can process in a sprint or something like that. And yeah, so there is kind of a delayed response in terms of updating the throughput on an operator, because those requests are set and then they're processed perhaps in the next processing window. So there's some latency between the computation of what the target backlog would be and then the response from the operator. So getting that tuned is a matter of testing, and there's some hand testing to be done.